About 4 years ago, I received an email out of the blue. The heading on the email was "The kids must be smarter," and the email read thus: "You might remember a puzzle about a pump station on a river and minimising the length of pipe to feed 2 towns. I seem to remember the maths whiz amongst us not being able to solve the problem using mathematical minimisation techniques, while the graphical solution is very simple. I used the problem in a competition in our office newsletter this week, thinking it would only be those who took the graphical approach who would find the solution. Much to my surprise, within 2 hours the attached solution was submitted. The winner gets a bottle of vino for her efforts. Regards." I received this email in 2005 from a mate who had been the groomsman at my wedding in 1974. The story itself goes back to 1968, when I was in the first year of a pure science degree majoring in mathematics, and he was in the first year of a Bachelor of Electrical Engineering degree. By 2005, I was a retired school principal, working part-time doing what I love most, that is teaching high school mathematics, along with some tutoring in mathematics education at the local university. He was by now a senior partner in a large firm of consulting engineers. Here then is the problem that I'd first been shown as a first-year university student back in 1968. Have a look at the diagram. We've got a farmer who wishes to build a pump station along the irrigation channel to supply water to both tanks A and B. I think the original problem was about towns A and B and a water supply, but anyway, we'll go by what we've sent here. In order to minimise costs, he needs to locate the pump station so that the total length of pipeline is minimised. Where should he locate the pump station? Well, simply, all we really want is the ratio of X to Y. Solutions, including reasoning, can be submitted. The solution will be provided in next week's office newsletter. Well, back in 1968, we couldn't see the point of wasting time on a calculus solution, which would be very long and tedious. Simply, the shortest distance between 2 points is a straight line. So let's take A dash, the reflection of A in our irrigation channel, draw a straight line from A dash to B, and where that straight line cuts the irrigation channel, that's where we'll locate the pump station. Well, from similar triangles, the ratio of corresponding sides is the same, so ratio of side X to side Y is equivalent to A over B, and of course we can locate the pump station. Well, we've solved the problem, and it was time to go to the regatta for a cold amber fluid, but unfortunately the people in the engineering department didn't pass him on this. He was supposed to solve it using calculus techniques. Well, my mate had been searching for 37 years for a calculus solution to this problem. He'd actually put this problem in office newsletters a few times over the years, and the only solutions he ever received were ones based upon geometry, as we've just seen. And then in 2005, one of his female graduate engineers came up with a one-page solution. So let's have a look at this solution now. One might just note that at the top of her one-page solution, she made a note that the project was a non-recoverable waste of time, and the subject was a brain teaser, dated the 19th of October 2005. Right, any good solution has a nice little diagram at the top to refer to. We're trying to minimise the length of the two hypotenuse of these two triangles. Well, the hypotenuse squared, sum of the squares in the other two sides. So we can see the total length is the square root of x squared plus a squared. It's the hypotenuse of the smaller triangle in this diagram, plus the square root of y squared plus b squared. Well, a and b are constants. If we're going to use calculus, I'd much prefer to have L as a function of one variable only. So we can replace y by considering the whole distance between the projections of these tanks on the irrigation channel. The total distance is z. Z's a constant. If z's x plus y, y can be written as z minus x. Okay, we'll make that replacement. And we then use the chain rule. And marvels upon marvels. We've got dl dx. Notice we can replace that expression involving x squareds and z's back with y squared plus b squared. What do you reckon? Did you like the Mozart while you were reading through the solution? You notice that the maximum and minimum occur where the first derivative is 0. And if we make that 0 and then square both sides, get rid of the square root sign, remove the brackets and expand. Notice that x squared over y squared is a squared over b squared. Well, you can forget about any negative solutions here when we're talking about distances. So it just means that x over y is a over b, which is what we got a while ago, just using the fact that the straight line's the shortest distance between 2 points. Oh, like any good teacher, I can't resist but follow up a teaching point by giving an exercise for the student to practice in what they've learnt. So how about trying this one for yourself? 2 posts, one 12 metres high and the other 28 metres high, stand 30 metres apart. They are to be stayed by 2 wires attached to a single stake, running from ground level to the top of each post. Where should the stake be placed to use the least wire? I'm sure you can work that out, can't you?